All right, this is Visual Minteq, the entry sort of splash screen when you open it up and get it going. First thing to notice, there's top menus and there's a bunch of things on the bottom. The top things are, I'll just go through. File is where you would save a file after you've made it if you wanted as an input parameter with parameters, or where you could also load one if you had saved it. Parameters are where you can specify information about the solution that you may or may not know. Solid phases and excluded phases. Solid phases are solids. Sometimes infinite means a solid that there's an infinite amount of. It will dissolve until equilibrium is achieved. So if it's very soluble, you could dissolve a lot of it. Finite means you can dissolve some amount, but you can only dissolve what you added. So if you know a mass, for example, but no, there's not more than that in the system. If it wanted to all dissolve, it could, but not more than that. Possible means it can form from solution, meaning if you have a bunch of things in solution, if there is no possible solid phase specified, it cannot precipitate. It may tell you it wants to, but it will not allow those solids to form unless you specify them as possible. Excluded species are things that you will disregard in equilibrium calculations. Adsorption is how we deal with surface reactions, and gas, we'll go through that maybe later. Gases are the partial pressures of gases that can equilibrate with the solution. Redox couples can be specified so that you can see what those, how for example, a chemical element like carbon would speciate between different oxidation states as a function of redox potential, for example. Sweep allows you to run many problems in a row and sort of see how things change over time. And database management is where you can look for the equilibrium constants that it's using once you've put in something. There's nothing here until you give it something that's in the solution and it knows what it needs to consider. So first and foremost, if we want to add a component is sort of a chemical species that, or usually it's listed as a chemical species, but what it represents is a family of species of similar form. So for example, CO3 minus 2 is the component carbonate, which is a certain amount of carbonate, but it includes carbonate, bicarbonate, carbonic acid, and PCO2, the carbon dioxide in the air, that all are in equilibrium with the solution. And so we specify a certain amount dissolved of carbonate, and then it figures out what all those other things, how much of each one of those it is, and what the partial pressure of CO2 is, given that concentration of everything in solution. So a species is a specific form of something at a specific concentration. A component is a set of species together. And if you have a total concentration of them all together, like in this case, notice the unit here, molal, I can change that unit right here to millimolal, for example. And I could type in there, and I could add to list. It doesn't work if you don't hit add to list. Then the amount of carbonate in solution is now 10 millimolar for all the carbonate species. And the amount of each carbonate species would vary with pH. So if we want to deal with, we can have the pH calculated, but typically we fix the pH at a given pH because it works better that way. If we hit run, it will tell us what's there. Right? And if we run, now here's our output. All we added is carbonate, and we specified pH, so the hydroxide and the H plus concentrations are defined based on the pH that we specified. The fraction of carbonate, bicarbonate, and carbonic acid depends on the pH, and you can see both concentration and activity are given here in the output. The gases button tells us there's only one gas that's related to this, and that's CO2 at 3 milliatmospheres pressure. Now, if you click print to Excel, something great happens. It opens Excel, and what you'll see when you go open in that window of Excel, it'll have exactly what was there in that table, each of those species now, and their concentration and activity. The activity coefficient is the ratio between those, if you wanted to calculate what it was. In general, we're going to ignore that in our class. We can add complexity very easily to this just by changing it. So for example, we didn't allow, there was no cation in the system. So we don't really have a particularly meaningful calculation regarding what happens when there's different kinds of pH, solids that might form. So one thing we could do is add calcium, which we know can form calcium carbonate. If we add that to our list and run Minteq, we're going to get a different answer now. So if you look, what's going to happen is that, it takes a minute to run now, it's getting more and more complicated. We see that now we have a lot more species. Calcium, it turns out, can complex and form dissolved ion pairs with carbonate, bicarbonate, and hydroxide. So in addition to having a calcium ion concentration, we have all those other forms of calcium in the system. And we also have the carbonate equilibria. One of the things we can see, we have display saturation index. So in this case, red is, so these are all the solids. In this case, aragonite is calcium carbonate. Calcium carbonate is also calcite, and vaterite is also calcium carbonate. So one of the things to notice is there's 3 different chemical forms with the same formula, but different structures and different solubilities. Calcium carbonate with waters attached, the calcium carbonate XH2O, is a hydrated calcium carbonate that forms as an intermediate as calcium carbonates form. Lime and portlandite, or calcium oxide and hydroxides, you can see they're highly undersaturated. The blue text means the number of orders of magnitude difference between the saturation index, the ion activity product, which is the real concentrations in solution of those things, and the solubility product. So things that have a value of 0, the ion activity product equals the saturation, the KSP, the saturation product, and that would mean it would be green and it would be at equilibrium. Red means it's supersaturated. What you can see here is that it's supersaturated with respect to many different solids and undersaturated with respect to 2. Of course, in reality, only one of those solids would be most likely to form. Either it'll form fast and be the kinetic product, or it'll form slowly, potentially, and be the thermodynamic product. So the thermodynamic product in this case is calcite. It's the most supersaturated. And the thing that forms very quickly is the hydrated calcium carbonate, which is barely supersaturated. In this case, it doesn't allow any of those to form. That's why they stay supersaturated. But what we can do is we could adjust our input by going back to output and then back to input and specifying a possible solid phase. This will allow whichever one we want to be the one that precipitates. And if we said we think that, let's say, aragonite, we can go to aragonite there. When we put that in the list, we see the saturation product, and we see the delta H of reaction, which allows us to calculate things over different pHs. And we could say add here. And what that does is it says aragonite is going to be allowed to precipitate now. And now when we run it, we'll see something different happen. If you notice, what's going to happen here is now we get an extra box on the bottom. We have the species distribution we had before. We have the saturation index, and you notice aragonite is green because we allowed the constant calcium and the carbonate to be removed from solution by forming aragonite. That's what it means to be a possible solution. We also have this amount of finite solids. In order for aragonite to precipitate and remove stuff to equilibrium, a certain amount of aragonite is formed, and this is how much? 2.88 times 10 to the minus 3 moles per liter. And then we have this equilibrated mass distribution, which says for calcium we have this much dissolved at the end after things precipitated, right? And because we allowed it to precipitate, it's a smaller amount than the 3 millimoles we added. In fact, only 3.7% of what we added to the solution as calcium stayed in the solution, and the rest, 96% roughly, was precipitated as that calcium carbonate. Because there was more carbonate than calcium, we see the carbonate still 71% stayed dissolved and only 28% precipitated. Right, if we print to Excel here, we also are going to get that table here, just the way it looks in Excel. So what we can do in Excel is print. You notice it gives you that output, but it does not tell you the conditions that were used to generate it. So one of the things you'll want to do in Excel, or take these little tables as you output them and make sure you write what you did in order to get them, so you can keep track of it and keep going. If you go back to the input menu, we could also change things. For example, at pH 8.3, we precipitated most of the calcium, right? All but about 3%. But let's say we change the pH to 7. So we hit 7, we enter, and we run. And here, when we run, it's not going to necessarily have the same values, right? We know from Le Chatelier's principle at lower pH, we get more of the carbonate turning into the bicarbonate and carbonic acid, so the amount of carbonate in solution is lower. And what that ultimately means is we have less supersaturated. So now if we look at our amount of finite solids, we get some amount, and our mass distribution is now, instead of calcium only 3% being dissolved, it's 74% being dissolved. And we could go back to the input conditions and say 6.8, for example, run Minteq. And notice what happens now. Now that button of how much solid precipitated disappeared. Why? Well, in this case, we're no longer supersaturated with respect to aragonite. We're barely undersaturated, but a little bit. And we're barely oversaturated with respect to calcite. What this really means is that aragonite couldn't form at pH 6.8. To put that into perspective of why that might matter, aragonite is what coral is made out of, for example. So if you are undersaturated with respect to aragonite, that's the equivalent of you trying to survive after your bones are no longer working. So corals don't do well at lower pH. You could also look at other variables here. We could also change temperature, because it turns out calcium carbonate has a temperature of things that actually varies more significantly. So if we increased our temperature to 40 degrees C and then run, we could see what happens. And now we have a saturation index that's saturated. So in fact, one of the interesting things, this mineral precipitates better. A solid is easier to make at high temperature than at low temperature. Now, let's put it back at 25 degrees C. If we wanted to do a sweep, just to show you how that works, here we input our sweep conditions. Our sweep is essentially just like a sequential set of things we want to vary. So the best way to think about it is as a titration, but where you don't necessarily, the titration button, you add solution and certain amounts of that solution, so you can have whatever you want in it and titrate with it. But if we just want to titrate with acid or base, we could titrate this way, where we just do, for example, we want to do 100 problems, starting at 2, and then every 0.1 pH units, we're going to do it again. So we'll calculate the speciation at pH 2, then we'll go up to 2.1 and 2.2 and 2.3, all the way up 100 times. So basically from 2 to pH 12. And then we can tell it all the stuff we'd like to have as output. If we want to know the carbonate, if we want to know the total amount of dissolved carbonate in the system, we could have also the amount of the concentration of that specific ion. We could have the concentration of H2CO3. We could have the concentration of H bicarbonate. So those are those things. We could also, for example, say, since we have aragonite that we're going to calculate saturation product for, right, we could calculate the saturation index of aragonite and the concentration of aragonite. So theoretically, because we're going to allow aragonite to precipitate, its concentration will depend on how much it was saturated. So then we could hit save and back. And now when we run, it's going to run those 100 problems in Minteq. So it's going to literally do some, thousands to hundreds of thousands of calculations to solve each thing, and do that 100 times to solve the system in general. And so it takes a while when it sits here doing all that math. And then when we get to the output, we'll have each run will then be displayed as its own output. As soon as it's done here, I'll show you. So here, if you notice, we have a new drop-down box for each one of those 100 problems. Since we did 100, we have something we could click on. We see how long it took, all this stuff. We see this is the pH 2 sample, and so forth. And we have all these species. We have, in this case, we have saturation index. Everything's undersaturated under acidic conditions, and so forth. We can also hit selected sweep results, and now we have, for each pH, the total carbonate dissolved, the CO carbonate concentration, the H2CO3 star concentration, the bicarbonate concentration, and the amount of aragonite saturation index, and the amount that was precipitated. So if you click on this, print to Excel now, and go over to Excel, we can actually see what happened. So here we're getting this spreadsheet now where we could actually calculate and see the concentrations. And one of the things you see is under certain concentration range, you see in general, if we look here, the concentration of our 3 carbonate species as an example. Really, most of our carbonate species is one of those things, not all of them. Okay, so there's going to be different, as a function of pH, different ones will be common. And because concentrations vary so significantly, you'll plot those often on logarithmic scales. You can see that aragonite starts out undersaturated. So acid is bad for calcium carbonate shells. And you can see pH 6.9 is the lowest concentration, at least for the system as we've described it, that we could, the lowest pH, or the highest pH, I guess, where aragonite would form or wouldn't form. So if the system was below pH about 6.9, at least with these concentrations, the system, we would have really no way for aragonite to form. And as we get to higher and higher pHs, you see the saturation index stays the same, because what's happened is it's precipitated increasingly. Column H here is the amount of aragonite precipitating. It's precipitating more and more and more until, to help maintain that solubility, so that the aragonite KSP, the solubility product or saturation index, and ion activity product are equal, which means it's perfectly saturated. Okay, so if we were to plot this, one of the things to realize is these are the units in whatever unit in moles per liter, or saturation index, which has its no definition, and this is the total species dissolved. But they don't really, but it takes 2 lines. And if you're used to Excel, what you'll realize is that is a subpar option if we want to think about. I'm actually going to just plot the first set here, so we can look at those concentrations varying. So here's our plot. Now we have the total dissolved carbonate in solution. You can see that once we get precipitate, the total amount of carbonate in solution is dropping. If we're at low pH, it's mostly the H2CO3 star. We can see the bicarbonate is what comes in commonly, and the carbonate, even though our equilibrium and everything was written in terms of carbonate, at least from pH below 9 and above or so, there's really no carbonate that's it's still in solution. It's a relatively minor component. If we were to plot this on a log scale, we can double click on that axis, and you can sort of see how that looks in those sorts of units. Because, you basically think of these, any number that's in that less than 10 to the minus 10 is impossible to measure. But now you can sort of magnify those low concentrations so you can see what they are a little bit better. And we can interpret that information as such. So that's basically what we want to go through on our first run. So with that, I will stop recording.